Okay, let's unpack this really fascinating stack of sources you shared.
Yeah.
What immediately jumped out at me is how you've connected these two things that, well, they seem like totally different worlds, right? You've got the real nitty-gritty of food spoilage on one hand, and then these pretty powerful ideas from higher level math on the other.
It really is a fantastic example, isn't it? It shows how these, sometimes abstract mathematical tools give us this essential quantitative way to look at everyday problems. Your sources specifically dig into differentiation and integration, key calculus concepts, and how they apply directly to things like microbial growth in food, and even aspects of packaging design, too.
Right, so that's our mission for this deep dive then, exploring that specific relationship you found in the sources, connecting calculus principles to, well, the rate microbes grow in food and how that affects packaging. Feels like it could be one of those real aha moments, where the math suddenly clicks in a new context.
Absolutely. When we start looking at food spoilage quantitatively, one of the first things we need is, well, how fast is it happening right now? And that's exactly where differentiation comes in. Your sources make it clear. Differentiation lets us measure the instantaneous rate of change. In this case, the rate of microbial growth.
Okay, so instead of just saying, oh, the milk's going off,
Yeah.
differentiation can actually put a number on how fast those bacteria are multiplying.
Mm.
Like right now, at this temperature, in this specific carton,
Precisely.
that level of detail seems incredibly useful for, well, prediction and maybe control.
Exactly that. It's about capturing the speed at one specific moment. And why does that matter? Like the sources highlight, knowing that instantaneous rate lets scientists, engineers, whoever, pinpoint critical moments.
Hmm.
They can see how quickly things are going downhill, compare how well different preservation tricks work at slowing that specific rate down.
Mm.
It takes you beyond just like an average speed over a few hours to the actual change happening second by second, almost.
Okay, right. So differentiation is like the speedometer for spoilage.
Mm.
Makes sense. What about integration then? Where does that fit in based on your sources?
Well, if differentiation gives us the rate at a specific point in time, integration lets us step back. It looks at the accumulation or, the total change over a stretch of time. Think of it like going from the speed reading back to the total distance you traveled.
Right.
So for microbial growth, integration could calculate the total bacteria that have built up over, say, a few days in storage using that changing rate information.
Ah, okay. So the total bacterial load after maybe 2 days in the fridge, that clicks. And your sources also linked integration specifically to volume of food packaging design. How does that connection work?
Yeah, this is where it gets really practical and honestly quite interesting. Integration is fundamental for calculating areas and volumes, especially when you have shapes that aren't just, simple boxes or cylinders.
Oh.
As your material shows, designing good food packaging isn't just about making something the food fits in. It's about optimizing material, sure, but also ensuring enough headspace, that empty bit at the top,
Yeah.
for things like gas flushing or maybe product expansion. And it has to account for potentially weird shapes of the food itself.
Like designing a plastic tray for some oddly shaped piece of cheese,
Right.
or figuring out the exact volume for soup in a curved container.
Exactly. Or making sure there's enough room if it expands when frozen.
Right.
Integration lets engineers calculate those volumes with real precision. It makes sure the packaging is efficient, protects the food properly, including leaving that vital headspace, which might even be influenced by potential gas produced by microbes.
Oh, interesting connection back.
Yeah, and it minimizes waste. It connects understanding the tiny microscopic spoilage rate to the big physical design of the container itself.
Okay, so let me see if I've got this right. Differentiation tells us how fast spoilage is happening now, giving us insight into the process.
Yep, the rate.
And integration tells us how much, like the total accumulated spoilage over time, and also how much space is needed for the packaging design. To handle the product properly, maybe even considering the spoilage itself.
You've got it. That's precisely the connection the sources make. It shows how these core mathematical ideas provide this quantitative framework, not just for modeling a biological thing like spoilage, but also for designing the practical solutions around it, like the packaging, all grounded in numbers.
So what this deep dive, really guided by the sources you shared, shows us is that these sometimes abstract mathematical concepts, differentiation, integration, they're not just for textbooks.
Not at all.
They're incredibly powerful practical tools. quantitative tools for analyzing, predicting, and even designing things to tackle real-world problems like food spoilage and how we package it.
Which really leads to a final thought, doesn't it?
It does. And this
Okay.
is one for you, the listener, to ponder based on all this. Think about other parts of your life, maybe your work or studies, anywhere where rates of change or accumulated amounts are really important.
Mm-hmm. Could be anything.
Yeah, like tracking how fast a chemical reaction proceeds, or understanding traffic flow over an hour, or even planning how much of some resource builds up over time.
Yeah.
Could calculus, differentiation and integration be quietly working behind the scenes there too, providing the framework for analysis and solutions? Something to think